There is a persistent misunderstanding that escaping Earth requires a rocket to hit exactly 11.2 kilometers per second, as if escape velocity is a rigid physical barrier a ship must smash through to reach space. The truth is that 11 kilometer per second requirement strictly applies to unpowered ballistic projectiles, like a cannonball fired once from the ground. A vehicle with continuous thrust and enough fuel could theoretically climb into space at a crawling speed. But flying slowly uncovers the actual enemy of the launch, gravity drag. For every single second a rocket spends flying straight up, Earth's gravity relentlessly robs it of 9.81 meters per second of speed. To fight that downward pull, the vehicle has to constantly push upward. But as it climbs into the upper atmosphere and eventually the vacuum of space, there is no ambient air to push against. This is where Newton's third law of motion steps in. To move in a closed system where external forces are absent, a vehicle must create an action to trigger an equal and opposite reaction. Rockets operate as thermodynamic engines, forced to violently eject their own mass backward to survive gravity's relentless downward pull. Inside the rocket, the combustion chamber acts as a highly controlled bomb. Liquid or solid propellants mix and react, creating extreme high-pressure, high-temperature gas. The amount of upward force generated, what aerospace engineers call momentum thrust, is dictated entirely by how much of this gas mass is accelerated out of the engine. But simply burning fuel isn't enough. Left alone, an explosion creates chaotic, omnidirectional pressure. To achieve liftoff, this scattered thermal energy must be organized and accelerated downward to supersonic speeds. This diagram shows the mechanical solution, the convergent-divergent de Laval nozzle. It acts as a specialized hourglass-shaped channel for the exhaust. As subsonic gas enters the narrowing convergent section, decreasing area squeezes the flow. The gas accelerates until it hits the tightest point, the throat. Here, flow chokes, maxing out at the speed of sound, or Mach 1. Past the throat, the geometry flips and the nozzle widens. Because the gas is already moving at sonic speed, this expansion causes a rapid drop in density. The gas accelerates further, converting extreme heat into supersonic kinetic energy. Raw chemical combustion cannot lift a rocket on its own. It requires the precise geometry of this nozzle to act as a thermodynamic lens, focusing chaotic heat into a singular, world-moving push. As the vehicle climbs higher, the surrounding air gets thinner. The ambient atmospheric pressure drops rapidly, which throws the fixed physical shape of the nozzle out of balance with the outside environment. If the outside pressure is lower than the exhaust pressure, the plume experiences underexpansion. It balloons outward laterally as it exits. Because this expansion happens outside the nozzle walls, the energy pushes sideways instead of down, wasting potential thrust. Conversely, if the rocket is in thick, low-altitude air, the heavy outside pressure dominates. This causes overexpansion, physically forcing the exhaust plume to violently pinch inward. These pressure mismatches create highly unstable, repeating shock waves known as shock diamonds. If severe enough, the resulting vibrations can tear an engine apart, which is why engineers utilize altitude-compensating nozzle designs to survive the varied pressures of the ascent. Even with perfect thrust, the vehicle faces a physical limit: structural weight. Heavy metal tanks and complex plumbing require immense energy to lift. Carrying all this dead weight all the way to orbit is mathematically impossible. Engineers bypass this physical limit through staging. By stacking the rocket in discrete sections, the vehicle can consume the fuel in its lowest stage, then intentionally sever and drop those empty tanks mid-flight. Shedding that mass instantly spikes the vehicle's thrust-to-weight ratio. While shedding weight, the guidance system initiates a pitch-over maneuver. The rocket tilts slightly, allowing gravity to naturally pull its velocity vector downward. This gravity turn slowly bends the flight path toward the horizontal plane, keeping aerodynamic stress to a minimum while building lateral speed. Surviving the ascent is a constant process of adaptation. The rocket dynamically drops thousands of pounds of empty structure while deliberately bending its trajectory, stopping the direct vertical fight against gravity and instead accelerating to outrun it horizontally. Once the vehicle clears the atmosphere and enters low Earth orbit, aerodynamic drag drops completely to zero. The physics of the flight shift. By traveling fast enough horizontally, the curve of the rocket's fall matches the curvature of the Earth beneath it, establishing a state of continuous freefall. Up here, the primary currency of spaceflight is delta V, or change in velocity. Free from air resistance, every second of engine thrust converts directly into orbital kinetic energy, shaping the exact altitude and reach of the spacecraft. But there is a strict finality to this environment. The moment a spacecraft exhausts its meticulously calculated onboard propellant, it can never alter its path again. Its trajectory is then governed entirely by orbital mechanics and the pull of surrounding gravity fields. Reaching the stars requires the precise application of thermodynamics, harnessing Newton's third law to sacrifice thousands of tons of mass for the momentum needed to push back against the pull of a planet.